Have you ever wondered what makes the silicon chip in your phone so totally different from the copper wire in your wall? Well, the answer lies in this hidden world inside materials, and it's all governed by something called energy band theory. It's kind of like the secret language of electronics, and today we're going to break it all down. It really all comes down to a super simple question. We all know a copper wire is great for conducting electricity, and a rubber handle is great for protecting us from it. But why? What is actually going on at the atomic level that makes them so fundamentally different? That's the big question we're tackling today. All right, to get to the bottom of this, we need to zoom way, way in. We're going to see what happens when you go from just one single atom, all by itself, to what happens when billions and billions of them get packed together to form a solid material. This is where the magic happens, where individual energy levels transform into what we call energy bands. So picture a lone atom. Its electrons are stuck in these really specific, neat little energy levels. But the moment you bring another atom close by, their fields interact, and those neat levels actually split in two. Now, imagine scaling that up to a solid crystal with billions of atoms. Every single level splits so many times that they all just kind of blur together, forming these wide, continuous energy bands. But here's the really crucial part. Electrons can't just have any energy they want. In between these energy bands, there are these no man's lands, regions where no electron is allowed to exist. We call this the forbidden energy gap. For an electron to be able to move and conduct electricity, it has to get enough energy to make a massive leap all the way across this gap. The two bands you really need to know are the valence band. That's kind of like the home neighborhood where electrons are bound to their atoms, and the conduction band. Think of the conduction band as a superhighway. If an electron can get onto that highway, it's free to zoom all over the material and conduct electricity. The size of that forbidden gap between the neighborhood and the highway, well, that determines pretty much everything. You see, that one feature, the size of the energy gap, is like a personality test for materials. It's so important, in fact, that based on the size of this gap alone, we can sort all solid materials into three totally distinct categories. First up, we've got the easy ones, conductors, like copper. In these materials, the valence band and the conduction band actually overlap. They're practically merged, which means there's no forbidden gap at all. The on-ramp to the electron highway is wide open, so electrons can just cruise on over with almost no effort. That's why metals are such amazing conductors. Now, on the complete opposite end of the spectrum, you have insulators. Think rubber or glass. For these guys, the forbidden energy gap isn't a gap, it's a canyon. It's huge. It takes a massive jolt of energy to force an electron to make that jump. So under normal conditions, it just doesn't happen. No free electrons, no electrical current. Simple as that. And then, sitting perfectly in the middle, we find the heroes of all modern electronics, semiconductors, like silicon. Their gap is, well, it's just right. It's not a canyon, but it's not wide open either. It's more like a small hurdle. It's just big enough that electrons need a little nudge, say from the heat at room temperature, to get enough energy to hop over into the conduction band and allow a little bit of current to flow. So let's just lay it all out side by side here. Conductors, basically no gap. Insulators, a huge gap. And semiconductors, a small, manageable gap. It all comes back to that one simple property. How easy is it for an electron to get to that conduction highway? This single idea perfectly explains the behavior of everyday stuff like copper, glass, and silicon. Okay, so if semiconductors are in this just right middle zone, how do we make them truly useful? I mean, being kind of conductive doesn't sound like the foundation for a technological revolution. Well, this is where we humans get really clever. We figured out how to hack their properties with incredible precision. This trick is called doping, and it's exactly what it sounds like. We deliberately add tiny, tiny amounts of specific impurities into the pure semiconductor crystal. And when I say tiny, I mean it. We're talking like one impurity atom for every million silicon atoms. But that one tiny change has a massive, game-changing effect on the material's conductivity. So doping creates two main flavors of semiconductor. On one hand, you can add an impurity like phosphorus, which has one extra electron to donate. This gives you a surplus of free negative electrons, so we call it N-type. Makes sense, right? On the other hand, you can add something like boron, which is missing an electron. This creates a little empty spot or a hole. This hole acts like a positive charge as it moves around, so we call this P-type. All right, so now we have our custom-made materials. N-type swimming in electrons, and P-type full of holes. Now for the million-dollar question. What happens if we stick them right next to each other? You create the single most important structure in all of electronics, the p-n junction.
The second they touch, stuff starts to happen instantly. The extra electrons on the N side see all those empty holes on the P side, and they just rush across the border to fill them in. This little flurry of activity right at the junction leaves behind a thin layer that's been emptied out or depleted of any mobile charges. We call it the depletion region, and this region creates its own electric field that acts like a gatekeeper, controlling any further flow of current.
So, a depletion region, a gatekeeper. Why should you care? Because that little junction is everything. Just one p-n junction by itself is a diode, which is basically a one-way street for electricity. Start combining them in clever ways, and you get transistors, the tiny switches that power all computing. You get the LEDs that light up our world, and the solar cells that power it. It all starts here. And you know, this didn't just appear out of nowhere. The story really starts way back in 1833. But the real game-changer hit in 1947 at Bell Labs with the invention of the transistor. And then, just about a decade later, boom, the integrated circuit was born, and suddenly we could cram millions of those transistors onto a tiny chip. That moment was the launch of the digital age we live in today. So let's just connect all the dots one last time. It all starts with the quantum idea of energy bands. That theory explains the unique properties of semiconductors. Then our ability to engineer them with doping gives us the p-n junction. And that junction is the fundamental key that unlocks the entire world of modern electronics. There is a straight line from that core physics concept to the device that's in your pocket right now. Which, of course, leaves us with one final, really exciting question. This journey from understanding silicon's energy bands to creating the computer chip has totally defined the last 70 years. So what's next? What new material or what wild new way of manipulating these energy bands is going to unlock the next wave of world-changing technologies? The next revolution is out there, just waiting to be discovered.